Shall we begin? Well, we are. Do this in the years to come. But tomorrow, this is on the quiz, what I'm going to cover today. So I gave you that worksheet. All right, already threw a fit here. The program's not working. Um, this is our non-trig starting point, and it's really not a big deal. Really shouldn't be a big deal. This is on tomorrow's test. It's just two formulas. You are going to have to separate your brain. Half of the quiz tomorrow will be no calculator, and it's all the the worksheet I just gave you again here today, which I told you should be done. Actually, I should say 10 minutes, 10 to 15. I guess that's fine. But the front page is only 6 questions, but just showing the graphs for you, just to get you the ball rolling again. Then the back page is draw your own graphs, kicks or ticks, blah 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 blah. And then it shouldn't be a big deal that there's a handful of these questions as well, but this would be on the calculator part. Okay, because we'll get some decimal answers. And really, it's based off of two formulas today, and applications of trig. Which one's this formula? Well, I gave you the C, so that should give it away. What's that formula? Circumference. And then this is why you guys, and I picked this one because it's more relatable to our thing today, but we do got to remember that a diameter is 2 radii, right? So another possibility is pi times d, which is one that you more than likely remember. But it's not that it's wrong. It just 2 pi r. But then I'll tell you why you guys messed this up. What's the a stand for? Pi r squared. This is why people get these two all mixed up, because they have a 2, a pi, and an r in it. And then they get mixed up which one is which. This one is walking around the outer edge of the circle. If you were an ant, walk, 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 walk. That is a full walk around whatever size circle that is, depending on the radius. Whereas this one is all the space inside of the circle, and it's listed in units squared. Okay, but we're going to change it a little bit. So, and then I'll show you how this formula actually works. All right. So here's formula number 1: arc length. Arc length is just a portion of circumference. And you should understand, as you look at this formula, how this is 100% relatable to our circumference formula. And then how theta, as long as it's in radians, actually tells you what portion of the circle you walked around. But for the first part, let's look at this formula. S equals R theta. What is theta for a full circle in radians? 2 pi. So if 2 pi is the radian measure, then hence that is a full circle. Hence that is the full circumference of the circle, right? There's your full circumference formula. That's why I like showing that. What's half a circle in radians? Pi. So if I only go halfway around the circle, dang it, then that would just be r pi. And then whatever r is tells us what the length would be. Radius determines how far you walk around. What is 90 degrees in a radian format? So if I only rotated pi over 2 radians, I only go 1/4 of the circumference. Do you see how the radian measure actually gives you the fractional part that you're dealing with? All right, but that's the kicker right there. If theta is in degrees in a question, you must convert it to radians, and then you're good to go. All right. There's another way of looking at this, but I'll wait till area questions, area of a sector, to show you probably your geometry formula you had back in the day. Okay. All right. Okay. Let's get this over with, right? Okay, here's 2 questions. Why could you stop moving, Mr. S? Circle has a radius of very specifically 18.2 centimeters. Find the length of the arc intercepted by a central angle given. And then, so hopefully you got that down. All you really need is the 8.2, because I'm going to move over here and draw this for you, the first one. 3 pi over 8 radians. And I would hope that you know 3 pi over 8 radians looks like it's less than 90 degrees. Because what's 90 degrees as we just shared? What's 90 degrees in radians? Pi over 2, which is 4 pi over 8. How does he do that? Is that calculus? No, it's grade school fractions that Lexi Samuelis knows. There's her name again. I'm suing you, Dad. All right. So, yeah. So that's why radians tells us what fractional part we're dealing with. And plus, it's just, and I forgot to say this in the video. Radians really translate to real world values, correct? Because a radian is created by real world values. Remember that circle with a radius of 2 inches? And then I walked 2 inches, and then I snapped back. That is 1 radian. Radians come from real world numerical values. And since that's the case, radians can be used to find real world numerical lengths and or areas. So it's something else to say that your angle measure must be in radians. As long as it is, you're good to go to just plug and chug and press enter. Okay? So it's a good point to make. Degree measures are not related to real world. They didn't come from inches, feet. So you have to convert them into radians that do come from that. If I change the circle to miles, like that one that I had, 8-mile radius and then 8-mile arc length, snap back to the origin, you got 1 radian of angular displacement. A radian comes from feet, miles, inches. So therefore, you can use it to find feet, miles, inches, or inches squared, feet squared, miles squared when you talk about area. So, I don't know. It's not rocket science to know what to do here next. Boom. You must convert that angle measure that's in degrees. You must convert it to radians in order to use it in an arc length question. I think at this point I'll press pause for just basic note taking so we can move on. This is why this is on the test tomorrow, because it's really simple. All right. Oh, I guess I had the drawing here. Oh boy. Stopped it and then it's kicked out. Here we go. All right. Okay. Oh, this one's so silly. But I'm going to go ahead and do it. Shh. This one's really weird. I think I have a drawing of this over here. Let's see if I do or don't. I do. Okay, good. I took the drawing out of the book. The other hour I drew it myself. All right, it's kind of over here. And I guess I could do it again, but I'll use the book's drawing. So silly. Don't write the whole thing out. Obviously, it's a long, annoying paragraph. But what it says in a synopsis is, and I'm trying to show this in class with my fingers, Reno, Nevada, and Los Angeles are nearly on a direct north-south line of each other. Okay? So what we can do is take a cross-section out of Earth in a proper way, a two-dimensional cross-section, and we can have both of those cities on that circle. Does that make sense? Okay, and then that's what they do. And they say Reno is due north of the equator 40 degrees, or a latitude. That's what that means, a latitude of 40 degrees. Los Angeles is 34 degrees north. Who's the further north city, Los Angeles or Reno? Reno, all right? Because this is what we have here. There's that cross-section. There's that cross-section of Earth. And they do have the rest of this given, but just pretend that's a full circle that I cut out of Earth, and it just happens to have those two cities right above and below each other, because it's, that cross-section taken out right there of that longitude line. All right, but the latitude lines are the ones that, Anyway, 34 degrees. This is why we knew Los Angeles was south of Reno, or vice versa. Reno was north. And what's that little sliver in between that you can barely read? What's that little sliver in between? 6 degrees. These are so specific questions. But I guess if cities are directly north and south of each other, we can treat this as an R. Anyone? Arc length question. Okay, well, they do have to give you this. What is the average radius of the Earth down to the center? 6,400 kilometers. They decided to put this in kilometers. Okay, since it's an arc length question, I hope you understand what do I got to do with 6 degrees? Turn it into a radian measure, and it's a flat out plug and chug. R 6,400 times the angle measure in radians, which needs to be converted. So please understand the converting thing. I'll zoom in on this question here in a moment, but try to get the idea of gears going and how gears work and maybe start drawing them that this is a gear question. And then I have a trick question in a way. Look at those two gears. Which one spins faster, the top gear or the bottom gear? How do you mean? Do you mean linearly it spins faster or angularly? Ooh. So it just says it just spins faster. What are you talking about? Angularly, the smaller one rotates faster. Linearly, they spin at the same rate. Because linearly, that's the connection of the two gears. Don't they travel the same distance over the same amount of time on the outer edge? Of course. So when you look at this question, I'll zoom in on it and go back to the gears. Two gears are adjusted, so the smaller gear drives the larger one. If the smaller gear rotates through a 225-degree angle, through how many gears will the larger one rotate? First of all, will that number be smaller or larger? First, I got this wrong. Smaller. See, here's what's going on. Linearly, I tried to show this. I tried to draw this first hour. If this spins 225 degrees, I tried to make this like 180, right? Doesn't that look like about 180 degree rotation? And then 225, I don't know, somewhere around there is that's where that rotates. So that black line, no, I don't know why that went away. All right, that black line is the linear distance that's traveled on the outer edge, which, because the gears are connected, is the exact same, I hit red, the exact same distance that this travels. And I tried to make it look somewhat like that was like the same length. Doesn't that look like about the same length, the red and the black? But how far this rotates is from here to here, which kind of looks like it's just a shade bit over 90 degrees somewhat, right? So there's a big idea in 3-4, and I love this question to really make a note of it. You know, which one spins faster? You got to watch your language. What? Somebody swore? No. Is it angularly or linearly? I'm having trouble speaking today. Angularly, the smaller gear rotates faster than the other gear. Linearly, they are at the same speeds on the outer edge. Remember that. Okay, so I have some people rolling their eyes like, oh, just get on with it, Mr. S. All right, please. That was you too, and it was your eyes. And she goes, yes, please. That's exactly what I was saying with my eyeballs. Oh, students speak with their eyes, very much so. So I took the little gear, and I found that linear distance traveled, which is arc length. And what are these linear distances between black and red? Say, there's only two more letters. Same, for the love of dog. I ask these questions in this class, and this is all I get. I get blank looks and this. Very much so. Then, now there is something you'll figure out after I do this. That means for my red gear, I guess that's what we're calling it, the linear distance traveled, that red distance is the same but with a different radius, which will allow me to find what the angle displacement is. based off of this formula. Okay, but the problem is, what is this angle measure in terms of? What's that angle measure in terms of, which we don't have a great feel for anyway, like rotation? That's in radians. How do I turn that into degrees? Convert it through our conversion formula. Blah, blah, blah. Did my calculator work over there? Okay, 117 degrees. That looks reasonable based off my little lengths that I drew there. Please understand the difference between rotational distance moved and actual linear distance moved. That's in feet, inches, and miles. All right? All right. I'll pause that for a second for any questions. You may have thought of a faster way of doing this. It's actually just a proportional question relating to the radii in question. Really, what you could have done is take 225 degrees and multiplied it by 2.5 over 4.8 and gotten the same answer. Anyone? 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 That's ultimately what ended up happening. But anyway. I'm skipping. No, I'm not skipping this one. Then the last one. We know what area of a circle is, right? As a matter of fact, I bet you this is what you did back in the day. Area, lost my pen, area equals pi r squared. And I'm going to write this formula down, and you could use it or not. Actually, I'm going to show it in the next one. Area of a sector, I'm going to write it like that. And that's just a portion of the circle equaled area of the circle times what fraction of the circle you're dealing with. What's a full circle? How many degrees? 360. And then all you needed was the central angle that cuts that particular sector. All right, the central angle is the key. And you should see what that means in this. Like if this was 60 degrees right here, then you have 63/60ths of the area, right? It's just a fractional simple thing. Even in discrete class, we had a little fractional example of with what silly thing we're doing in class. So here's the formula. Then you'd be like, wait a minute, that doesn't look like what I expected it to become. Let's just put this down for a second and then analyze it when we have a full circle in radians. What's a full circle in radians, by the way? Not 360, tricked you. In radians, 2 pi. So if I take theta and I put 2 pi in it, and then move that r to be r squared over here, what's half of 2 pi? Pi. This turns into pi r squared when I throw a full circle. That's the whole area of the circle. What's half of a circle again? What's half of a circle? Pi. Dang it, that happens every time. That's infuriating. Now I have half of the area of the circle. And so on and so on and so forth. Same thing with sector length. Area of a circle is what this is, and when we put whatever radian measure in there, it already tells us what fractional part we're working with. So off to the right, I put the half r squared times 2 pi, and that turns into pi r squared, which is our formula for area of a full circle. Just trying to relate the two things. Okay, I already talked long enough. Here's this silly little piece of property. We want to find the area of it. And I can write this in two ways. I could go back to my old geometry days, or specifically with this formula, but what must the angle measure be in? What must the angle measure be in? Radians. So our new formula, it would look like this. I really hope you saw the old formula, but it's the same. R squared half theta. But I got to make theta in the radians. The old way you would have done this is say, okay, I have 15 degrees out of 360 degrees of pi r squared. And these are identical. Okay? One or the other, I couldn't care less. Problem is, if they give you the angle in radians, you probably got to stick with this one. Because then you might get yourself all discombobulated. This one's when back in the day, you didn't know what a radian measure was, and you didn't have these area formulas in terms of radians. You were just given angle measures with degrees, and then this is what you said. Okay, it's 15 3/60ths. That was not what was supposed to happen. This is 15 3/60ths of a full circle's area. It's a very easy way of looking at it. All right. But anyway, regardless of what you do, nope. Yeah. Oh, what's multiples of 3 mean? That is, I did look at the calendar. You do 3 and then what? 6. Then what? 9. Then what? 12. Then what? 15. Okay. End of movie.